Alright guys, welcome to this edition of AP Notes. We're going to talk about electrostatics. It's kind of weird today being in my classroom at 5 o'clock in the afternoon with nobody here, so no, there's no yanker to yell at. What am I going to do? So let's get started here and let's talk about electrostatics. When we talk about electrostatics, we're going to be talking about charged particles. And it's important that you know that opposites are going to attract and like objects are going to repel. You know this when we play with a balloon. So if we have our balloon and our hair here, when we brought that charged balloon up to it, actually that charged balloon is going to be negatively charged, there was an attraction between the balloon and the hair. That means the balloon was negatively charged and the hair was positively charged, so we saw that attraction. The reason that things are going to either attract or repulse is due to the parts of the atom and those charged particles within them. And there are three particles in the atom that you need to know. It is the proton, the electron, and the neutron. These masses are here for you to see. It will be provided to you on the equation sheet, and you will be using the mass of a proton, electron, and neutron. Right here, we're going to see the charge on an electron, proton, and neutron. And remember that charge, the symbol that we use for charge, is the letter Q. Q is an inherent property, and we know that a proton is a positive one charge. When we don't talk about what that unit is, and when we talk about it in terms of coulombs, that proton is going to have a charge of positive 1.6 times 10 to the minus 19. An electron has a negative 1 charge, so its charge value is negative 1.6 times 10 to the minus 19. And of course, we then have a neutral object, and it will have no charge at all. It's important for you to realize that a proton is much, much, much bigger than an electron. It's about 2,000 times bigger than an electron. However, that electron has the same magnitude of charge. It's just simply an opposite sign. The conservation of electric charge is one of our 4 conservation laws. By now, we have covered all 4 of them. I hope you remember them. The first one is conservation of mass. We have the conservation of energy, conservation of momentum, and now the last one is our conservation of charge. And basically what this means is that if I have an object right here that has a proton, some neutrons, some electrons, and so let's go 2 and 2, or 3 and 3, and these two come in contact, if I start off with a total of 6 protons and 6 electrons, after they interact, I still have to have the same number on each side. And so make sure you realize that I still have 6 protons and 6 electrons. They have just changed forms here. Kind of self-explanatory. I don't think you'll have any problem with that. We're going to talk about conductors and insulators. A conductor is a device that does transfer charge easily. Most metals are conductors. The reason that they are a good conductor is because they have lots of free electrons, and those free electrons make it easy for us to transfer that charge. An insulator does not transfer electrically charged easy, and again, the examples of that: plastic is not a good insulator. Glass, rubber, all of our plastics are not good insulators. There are 3 ways to transfer charge, and we did most of these in our lab that we did last time I saw you. The first one is charging by contact. So the first one is really easy. You're going to rub 2 things together, and it's the electrons that are getting transferred. Why is it the electrons that are getting transferred? There's a couple of reasons why. First of all, those electrons are on the outermost energy shell. They're far away from that nucleus, so they're able to be stolen easily. Also, those electrons are very small. It is easy for those electrons to go away because they can sneak out of there. And it's very difficult to overcome that nuclear force. Remember that the nucleus is the protons and the neutrons. There's no way protons can overcome that nuclear force in order to be transferred. So it is those electrons that are transferred out. The next thing we can do is we can charge by induction. What you need to know when we charge by induction, this is only going to occur with conductors. We're going to bring a charged object close to a neutral object, and it will induce a charge on the first object. For example, we have this. We have two metal spheres that are non-conducting. So we have some equal numbers of protons and electrons here. And I'm going to bring a positively charged rod up close to it. You can obviously see that these negative electrons zoom over this way. Our positives are going to get as far apart as possible. And so when I take these two spheres apart, we're going to be left with a negative charge on A and a positive charge on B. This says we have induced a charge. We did not touch this ball with our charged rod here. We simply were able to induce that charge. Again, only occurs on conductors when we look at that. The next one is charging by polarization. Again, this is what you did in the lab. This is going to occur with insulators. When we bring an object close to an insulator, the atoms are going to rearrange. And you saw this when we did the water and we did the balloon sticking to the wall. The easiest to see is with our water molecule, because if you remember, our water molecule has an oxygen and two hydrogens. These hydrogens have a partial positive charge, the electrons a negative charge, because all those electrons want to hang out with the oxygen. And so when we bring it up to a charged, negatively charged balloon, what's going to happen is these water molecules are going to rearrange so that those hydrogens are as close as possible. And so this is what we get there. Okay, you need to know those three examples of charging by contact, induction, and polarization. There have been a couple of free response problems where you have to identify these parts. So hopefully that makes a little bit of sense to you. All right, time for the fun math part. Here we go. The electric force. We're going to use the electric force as Fe. And so if we have charged particles, there's going to be an electric force between them. Because remember, a force is simply a push or a pull. And so if we have charged particles, we can obviously an attraction or a repulsion. We're going to see that push or a pull. Here's the formula for that electric force. It is K, Q1, Q2 over R squared. For this case right here, our K value is 8.99 times 10 to the 9th. Sorry about that typo right there. That should be to the 10th to the 9th power. However, on the multiple choice, you can round it and make your life easier. You can use 9 times 10 to the 9th when we do multiple choice problems. Most of the time, there's not a multiple choice problem with electrostatics on here just because the exponents are kind of nasty to do in your head. But every once in a while, they'll throw it on to there. Again, this formula should look a whole heck of a lot familiar to you. You should recognize this as the force of attraction when we have big G equals M1, M2 over R squared. This is yet another example of some common themes in physics that seem to repeat themselves over and over and over again. Remember, when we talk about forces, our SI unit for force is the Newton. This is where I stop and say, are there any questions? But there's no one here watching me, so I can't do that. This practice problem is going to be very similar to some ones you need to do on your homework, and I want to go through these steps one by one as we go through this, and hopefully it'll make a little bit more sense. The first thing that I want you to do when you do this is to identify which charge we're talking about, and it's going to tell us in the problem what we're going to do. We're going to look at Q3. So when we look at Q3, we need to look at the forces, or what's causing a electric force on that Q3. That'll lead us to the next step, is which to draw the arrows. Can't spell arrows, imagine that, on the charge we are talking about. And so since I'm looking at Q3, I'm going to pretend that Q2 does not exist. Will there be a force between Q1 and Q2? I'm sorry, Q1 and Q3. Well, are they charged particles? Yes. Will there be a force between them? Yes. And so how do we draw that direction of that arrow? This is a negative 8 microcoulomb charge. This is a negative 4. Negative and a negative, are they going to attract or are they going to repel? Of course, you know, like charges are going to repel. So from the one that I'm talking about, which is Q3, I am going to draw that force because it's going to repel. Draw it to the right. It's repelling. And I'm going to label this the force between Q1 and Q3. Hopefully that makes a little bit of more sense to you. And then now I'm going to get rid of Q1 and see how Q2 is going to interact with Q3. I have a positive and a negative. These are unlike charges. What do unlike charges do? They're going to attract. And so I will draw this arrow right here. I will label this the force between Q2 and Q3. The next step is to actually calculate what those forces are. And so as I calculate those forces, it becomes really simple because I know the formula. I'll calculate the force between Q1 and Q3, and that'll equal to K Q1 Q3 over R squared. Don't forget to square that R. Remember here, I'm going to put a little star in, don't put in the positives and the negative signs. Those positive and negative signs basically tell us the direction, and they kind of will screw us up. So we draw those arrows, which is step number 2, to determine the direction. So when you're plugging into this equation, you are not going to put in the charges. You're just going to simply do that. And that brings me to another thing, this micro. What the heck does micro mean? Micro is a really small number. So when you see micro, you know you need to put in a 1. At the end of the number, you're going to put a times 10 to the minus 6 on there. Micro means times 10 to the minus 6. You might see nano. Nano is times 10 to the minus 9. So as you do that, don't forget to put that value in when you do that. So when determining the force on Q1, Q3, I've got 8.99 times 10 to the 9th. I've got 3 times 10 to the, which is not Q1. That is Q2, so let me change this to the correct value, which is 8 times 10 to the minus 6 times my 4 times 10 to the minus 6, and the distance between them. I've got to do some adding here. 0.3 plus 0.2 is 0.5. Again, a common mistake people make is they neglect to square that value. So don't fall into that trap as we do this. I just thought of another problem with me doing this. Who's going to correct my math when I screw it up? I'm sure you will if I do this wrong. When I calculate this value, I get 1.15, so I'm going to write that down right there. I need to calculate the force between Q2 and Q3. Conceptually, you should see that this force has got to be, or probably will be, stronger. Why is it going to be stronger? Because it is closer. Hopefully you see that that is R squared, so that'll have a bigger impact than what our Q values are. And so we'll take our 8.99 times 10 to the 9th, we'll multiply that by 3 times 10 to the minus 6th, then we will multiply that by 4 times 10 to the minus 6th, and we'll do our 0.2 squared. And so we will plug that into our calculator. And again, I've got an error in my calculator, so let me redo this. I feel like I should be singing and dancing to you as y'all are waiting on me to plug into my calculator. When I do this math, I'm going to get 2.70 newtons there. Alright, the last step, which is down here, number 4. You're going to draw a free body diagram on the charge, which will allow us to see the direction of the force. This one's actually pretty simple because if we look at this and we draw our free body diagram on this charge, it's very easy to see that the force between Q1 and Q3 is positive, the force between Q2 and Q3 is going to be negative. So my F total is going to be the F Q1, Q3 plus the force between Q2, Q3, and as I plug in those numbers, I have to add the correct direction. So I'm going to have a 1.15 here, and then I'm going to have a minus 2.70 here. When I do that math, I get a total of 1.55 newtons, and that's going to be a negative charge. So basically what that tells me is that my overall net force, what is happening to this thing, is that I'm being attracted to the left at 1.55 newtons. Hopefully that makes a little bit of sense to you, because now we get to do the even harder stuff. Yay, the dreaded triangles here. As we do our dreaded triangles, we are going to follow the exact same steps. And so, of course, the first step is to draw, see which one we're looking at. We're looking at this Q2 here. We're going to draw the direction of the arrows. Will there be a force between Q1 and Q2? They're both positive, so of course there's going to be a force between them. It's going to repel, so I will label that the force between Q1 and Q2. Will there be a force between Q3 and Q2? Yes, one's positive, one's negative, so this one is going to go that way along the diagonal. So I'll label that the force between Q2 and Q3. So far so good, except I don't have some distances here. How do I calculate what that distance is between Q2 and Q3? Hopefully you can see that this is a Pythagorean theorem problem. And so that using the Pythagorean theorem will enable me to calculate what that distance is between the two. When I calculate that math, I get 0.60 meters. Again, the next step, to calculate the force between Q1 and Q2, which will be KQ1, Q2 over R squared. 8.99 times 10 to the 9th, times 65 times 10 to the minus 6th, times 50 times 10 to the minus 6th, divided by my distance, which is going to be 0.3 squared. When I get some math in here, I get a value of 324 newtons. 325 if I round to the whole number, because I'm going to be lazy and do that. Do the same thing between the force between Q2 and Q3. And so again, I'll have 8.99 times 10 to the 9th times 65 times 10 to the minus 6th times 86 times 10 to the minus 6th over 0.6. Don't forget to square that value. And again, as I plug into the calculator, I really should have some cheesy jokes to tell you, but I don't. So here we go. When I do the math, I get this force to be 140 newtons. Here's where it gets a little tricky because I can't add them. They're not on the same line. This one's going pure north. This one over here is going southwest. So what do? I go back to my little free body diagram here and yuck, yuck, and yuck. I get to use the dreaded T-chart. Let me go back. So sorry. And so when I do my T-chart, it's just a little method to help you organize your thoughts. I'm going to have X and Y components. I'll have the force between Q1 and Q2. And I'll have the force between Q2 and Q3. Let's do the easy one first. Look at this force between Q1 and Q2. It is going pure north. So as it goes pure north, sorry, I did that again. My X component will be 0. I'll need to put a positive 325 in that component. Now, what do we do with this nasty Q2, Q3 mess? And so if we look at this, I know what that is. I just calculated that. That is 140. But in order to plug in my T-chart, I need these components right here. In order to get those components, I need this angle theta. How do I get angle theta? Good old trig that never fails me wrong. And so if I can use the tangent is opposite over adjacent, I can calculate that angle to be 0.52 divided by 0.30. And I get a value of 60 degrees here. So then if I know this and I know this is 60 degrees, I can use sine, cosine, and tangent to get my components. As I do this one, I'm going to get 70, but be careful because this one is going down. So I have to make that component negative. Don't forget that. If you make a mistake on your internet homework, that's probably what you did. It's very difficult to find this. My x component is going to be 121. Of course, it's going to the right. So as I plug this now into my XY T-chart, I get 121 here, negative 70 here, And the last step is going to be to add up the columns. Add these up, I get 121. And if Cole was here, he could do this in his head, but he's not, so I have to do it calculator way. 255. Again, not my final answer because I have to put that x and y together. One last step. Start at the origin. Do x first, 121. Do y next, 255. My answer will be the hypotenuse and the angle that it makes with the horizontal. So I'll do 121 squared plus 255 squared equals c squared. And that should enable me to calculate the value that I want. And so what I get is a force of 282 newtons. And again, my answer is not complete without the angle. So again, I'll use tangent. And so I'll do the inverse tan of 255 divided by 121. So I get 282 newtons at an angle of 65 degrees north of east. Okay, we've got that number. What the heck does that actually mean? It means when I put this force together and this force together, the overall net force is going to be going this way at an angle of 65 degrees. Alright, I'm going to take a little pause break right now because my throat's sore and I want something to drink, and I'll come back with you in just a second. Alright guys, I am back. So what we're going to talk about next is the electric field. The symbol that we use for electric field is a capital E. Now, right now, we are in a gravitational field. How do you know you're in a gravitational field? If I drop my set of keys, do they float in the air? No, they go to the ground because we are in a gravitational field in which a force, i.e. the force of gravity, acts upon it. The same thing occurs with an electric field. Notice the comparisons between gravitation and this electrostatics unit. It's very, very similar. When we talk about an electric field, we're going to talk about a charged particle, some positive charge. Surrounding that charged particle is going to be an electric field. And so all the way around a charged particle is an electric field. Where is that electric field going to be strongest? If I look at this, is it going to be stronger here at point A or over here at point B? Well, obviously it's going to be stronger at point A because it's closer to that charged particle. So how do we define what an electric field is? An electric field is a region in space in which a test charge is Q0, will experience a net force. I want you to realize that a test charge is a teeny tiny positive charge that is used to determine the location within an electric field. Test charge, teeny tiny positive charge right here. And so what we'll have is around our charged particle, we're going to put this teeny tiny test charge, and that will enable us to calculate where what that force will be. As many times though, keep this in mind that the electric force is going to equal to EQ. Don't forget that formula because a lot of times that formula becomes very important for you to use. Our SI unit for the electric force is newtons per coulomb. The electric field is also a vector, so we have to determine the value of what that direction will be. The way we do that is if we have a positive charge and we put a positive test charge, what is positive and positive going to do? It's going to repel. So my electric field will point away from a positively charged object. If I have a negative charge producing the electric field, put a teeny tiny positive test charge in there, negative and negative, my electric field will point that way. So it will point towards that. So again, away from a positive charge towards a negative charge. There's an alternate formula for the electric field, and I want to show you how that is derived because it's actually pretty simple. We know the electric field is the force that a test charge experiences. We just spent the last 20 minutes learning what the electric force is. Well, what is this force going to be between these charged particles? That force is going to be K, Q, QO over r squared. And so I can take that and plug it in over here. When I do that, I'm going to get k q qo over r squared. All of that multiplied or over 1 over r squared. Nope, didn't do that right. I'm so sorry. That over QO. Wow, I'm like tired. And so, right there, plug it into that formula, not the other one. What happens then is this QO will cancel, and so I'm left with this formula that you will use a whole bunch until you get sick of it, which is KQ over R squared. Now pay attention to these Q's. This is the Q that produces the electric field. And this Q up here in my alternative formula is the test charge. So depending upon what you're given in the problem will determine which value that you use. Again, over r squared, our K value has not changed. It's 8.99 times 10 to the 9th. All right, typical problem here. Find the electric field at point P. We're going to work through this just like we did before. Step number 1. What is our steps here? Step number 1, draw the direction of the electric field. So how are we going to draw that direction of that electric field? At point P, we're going to put the test charge. That test charge is always a teeny tiny positive charge. So as we look at this, is there going to be an electric field produced because of Q1? Of course there is, because it's around a charged particle. This is negative. My test charge is positive. So what then is going to be that direction of that electric field? Negative and positive, it's going to go that way. My E1 will be going to the left. Okay? Is that going to be the only charged particle producing an electric field? No, we got Q2 over here, and it's a little bit further away, so of course that electric field should be weaker. So let's look at the signs. I've got a positive and a positive. What is it going to do? Hopefully you know, positive and positive are going to repel. So my E2 is going to be going to the left, knowing that I'm drawing that direction of the electric field at our point P, wherever we are talking about. Alright, so step 1 again, draw those directions. Step 2, we need to calculate what that electric field is going to be. We just did this. We just practiced this. We're tired of it. It is KQ over R squared. And so this E1 is going to be due to charge 1. Again, 8.99 times 10 to the 9th. Times my Q1, which is going to be 25 times 10 to the minus 6. Remember that micro, times 10 to the minus 6. Notice I did not put in the signs. Again, I did not put in the signs for the same reason I didn't before. Step number 1 had me draw the direction of there, and we'll use that direction in just a minute. Okay, I get a humongous number here, so I'm going to double check my work to make sure I didn't plug it in the calculator wrong. But usually these electric fields are really, really, really strong. Or actually a large number. Okay, I did it right. 3, 6, 7, 8. I got 5.6 times 10 to the 8th. Huge number. Newton per coulombs there. We're going to do the exact same thing. We have to calculate what that E2 value is. This time will be KQ2 over R squared. 8.99 times 10 to the 9th times 50 times 10 to the minus 6th divided by 0.08 squared. Plug that value in our calculator. You'll get very good at plugging in 8.99 times 10 to the 9th because we will use that a lot. 6, 7. A lot smaller number, 7.0 times 10 to the 7th Newton per coulombs. We do that. Step number 3 again, draw that free body diagram that will allow you to see which direction everything is going. And so as you can see from my point P, both of those are going to the left. So if I calculate E total, I'm going to add them up, but now when I put them in, they have to be negative. The reason that they're negative is that they are going to the left. And so when we add those numbers, and I'm plugging in everything that I have on my calculator, so my significant digits are going to be off just a hair, I get 6.3 times 10 to the 8th Newton per coulombs. Again, negative sign indicating that they're going left. This, what we're just doing, is exactly what we did with the electric force. The only difference is with the electric field, my formula changes just a hair. But again, everything in the steps, all of that, exactly the same. Plug it in and do this. Using the information from above, if the electron is placed at point P, what is going to be the acceleration of the electron initially? Alright, so here's my little picture. I have this point P, and I'm going to place an electron right there at point P. Well, what causes acceleration? Hopefully this has been beaten into your head until you can't think anymore. A force causes an acceleration. Do I know the mass of an electron? If I flip back to the front, an electron is 9.11 times 10 to the minus 31. Really sad I have that memorized, but I do. I'm looking for I'm looking for A, so I somehow need to get F. Okay, I can place an electron because I know the charge of electron. It's 1.6 times 10 to the minus 19. And I can do all of those freaking little steps that I just did at earlier in the day. Or I can make my life easier to remember the easy formula. Remember that the force is equal to EQ. Remember I told you that would be coming in handy in a little bit? Did we just calculate that total electric field? Absolutely. I can plug this in. Do I know the charge on an electron? Absolutely. 1.6 times 10 to the minus 19. So I can take these numbers and I can multiply them together, and I'm going to get a force of 1.0 times 10 to the minus 10 newtons. Plug that in over there, and that will allow me to calculate that acceleration of that electron. Even though the force doesn't seem very big, when I do the math, I get a humongous acceleration. Oops, so sorry. That went too far. You really don't want to do that part yet. It's just like in class. Miss Hood can't pay attention. We'll see what she's doing here. Alright, here we are. Back to this, like an acceleration of 1.1 times 10 to the 20th meters per second squared. Use acceleration here. Back in history, and I know it's hard for y'all to see, but if you look up into my room and see that old-fashioned TV that is huge, the reason that it's huge is there's a cathode tube ray behind there, and this is the actual process that we were able to see TVs back in the olden days, because they'll be back in your old days. The electrons are placed in that electric field and they shoot forward. But nowadays, we're all in HD and things are a little bit differently, and I don't really know the answer to that. Last little bit before we are finishing up with this part of it, we're going to talk about electric field lines. Electric field lines are going to show the direction of the electric field. Notice that these are two, a positive and a negative charged particle, and they're going to show the attraction between these two particles. These are two negatively charged particles, or positive, whatever, they're like charges, so they're going to repel. As we draw these electric field lines, there's some rules that you have to know. The first rule you need to know is that the arrows always point from the positive and go into the negative. Now this is kind of small to see, but the arrows always leave the positive and they're going into that negative. The number of lines will be proportional to the charge, and I'll go more in depth of what that means in just a second. Our lines can never intersect. Like charges repel, and like charges attract. So how do we do this? If I have a positive 2Q charge here and a negative 3Q charge here, we know that they're going to attract. So I'm going to start drawing some lines. I'm going to go from the positive to the negative, from the positive to the negative, from the positive to the negative. And so now I look at this. Do they leave the positive, go in the negative? Yes. Is the number of lines proportional to the charge? So the easiest way to do this is to look at the ratio of the charge. I have a 2Q to 3Q charge. And so I'm going to count the number of lines that are leaving the 2Q charge. There are 4. In order for my ratio to be the same, what does this number have to be? Hopefully you can see it has to be 6. So that means I have to have 6 lines going into the 3Q charge. Right now I only have 1, 2, 3, 4. So I need to draw 2 more lines coming in from God knows where, and I'm going to draw those arrows going into the positive charge. How many lines do you have to draw is always the question. It doesn't matter. You could have gone 2 and 3 and been correct. You could have done 14 and 21. It doesn't matter as long as that ratio is correct. One more example that I want to show you. If I have a positive 5Q and a positive 10Q here, again, 1, 2, 3, 4. I'm going to draw 4 lines just because I want to draw 4. Positive means they're leaving the positive. So in order to make this work, hopefully you can see that this is 5 over 10 has to be 4 over x. What do I need to put there? Hopefully you see there's 8. 1, 2, 3, 4, 5, 6, 7, 8. And again, they will leave that positive charge. I'm going to stop here for today. I'm not sure I'm going to get the rest of this posted because I'm tired and I have other stuff to do tonight. So hopefully this is going to work and this will help you. Again, go through these notes. If you have any questions, come see me in class. Ask your questions away. And I hope you enjoyed this new version of AP Physics. Thanks for listening. Testing 1, 2, 3, test. This is a test. Testing 1, 2, 3. Testing with me talking. Is this going to work?